Greetings students and welcome to my lesson on weird types of differential equations. You don't usually study these types of differential equations in early or even intermediate undergraduate courses. They tend to come up in areas of research and upper level courses on applied math. Now by weird differential equations, I'm really going to talk about four weird types of differential equations: delay differential equations, integro-differential equations, fractional differential equations, and stochastic differential equations. We'll start by discussing delay differential equations. When you look at dynamical systems consisting of a single differential equation, you conventionally think of an equation like dx by dt equals f of x comma t. The differential equation depends on the value of t and the value of x at the present time, at the current time. However, what if in addition to my differential equation depending on x at the present time, it also depended on the value of x at a previous time, let's say tau seconds before the present time t. In that case, we could write our differential equation as dx by dt equals a function f of x at the time t, x at the time t minus tau, and t, where x of t minus tau represents the value of x that occurred tau seconds earlier. This differential equation, which depends on the value of the dependent variable x occurring earlier, is called a delay differential equation, or DDE. A delay differential equation dx by dt is a differential equation that depends on the value of x sometime in the past. Now what I've written up here and called a delay differential equation isn't the most general way to describe a delay differential equation. In fact, there's actually three types of DDEs. The first type is a DDE with continuous delay. This DDE depends on x, t, and the sum of all possible past values of x. And if you want to sum so many values, then in general you can write that as an integral. The integral from negative infinity to 0 of x of t plus tau times d mu by d tau with respect to tau, where mu is some function of the delay tau. The second type of DDE is the type we wrote above, where the delay is fixed and discrete. Of course, you're not restricted to a single delay. You can have multiple delays in your system, tau 1, tau 2, all the way to tau n. The third type is one in which you have a scale delay. Now, what do I mean by this? Basically, your DDE depends on x of t, the value of x at time t, as well as a previous value of x corresponding to lambda times t, where lambda is a constant between 0 and 1. A special type of this equation is called the pantograph equation, given by dx by dt equals a times x of t plus b times x of lambda times t, where a and b are some real constants. Now, how do you solve a delay differential equation? I won't go through a complete example here, but I'll briefly illustrate what the process looks like. Say I have a DDE with a discrete delay tau, like the simple DDE I described earlier on in the video. I'll call this equation 1. To start solving this DDE, I need to first specify an initial function from negative tau to 0 as opposed to an initial condition at t equals 0, for instance. And why do I need to specify this initial function? Let me explain this on the side. Say I had to solve this DDE, and I only had the value of x at time 0 as my initial condition. Suppose also that my delay tau was 5. Then, in order to determine the value of dx by dt, and by extension x of t at the time 1, I would need the value of x at time negative 4, according to this DDE. However, I only have the value of x at 0, I don't have the value at negative 4. So specifying x at 0 is simply not enough to solve this DDE. I need to specify what the entire function looks like from negative 5 to 0. Which is why I need an initial function as my initial condition instead of an initial point. So given this DDE and initial function, what we can do is substitute phi of t minus tau for x of t minus tau into equation 1, with t minus tau varying from negative tau to 0. Then, with this function plugged in, we can solve for x of t from t equals 0 to t equals tau. And once we obtain x of t from 0 to tau, we can then plug that in as x of t minus tau, and then solve for x of t from tau to 2 tau. Then we can keep repeating these steps, plugging in our previous x in place of the x of t minus tau, and using that to solve the differential equation and obtain a full value of x that's tau units of time in the future. This full method, by the way, is given a special name. It's called the method of steps. Another type of weird differential equation we'll go over is the integro-differential equation. As the name implies, this type of differential equation contains both the derivatives of the function of interest and the integrals of the function of interest. For instance, if I have a first-order differential equation in terms of dx by dt, an integro-differential equation could look something like this, where dx by dt is f of x comma t plus an integral term from t naught to t of another function g of s comma x ds. Except for really simple cases, it's not that easy to solve integro-differential equations by hand. But in cases when you can determine the solution analytically, like simple linear differential equations, you can use integral transforms like the Laplace transform to find the answer. I should also note that we don't necessarily need to have a first-order integro-differential equation. We can just as well have second or higher order or even partial integro-differential equations. The next type of weird differential equation we'll discuss is the stochastic differential equation. Consider our typical differential equation dx by dt equals some function of x and t. If I add a term sigma of x and t times an epsilon of t, where epsilon represents a white noise term, then I get something called a stochastic differential equation, which is a differential equation that depends on some random fluctuating or stochastic process. Solving stochastic differential equations involves using techniques developed in stochastic calculus in combination with numerical methods. We won't go over those here since our goal with this video is just to introduce these weird types of differential equations. And the last type of differential equation I'll discuss is a fractional differential equation. As the name suggests, this is a differential equation which involves the fractional derivatives of an unknown function. To see what this means, let me give a very brief pep talk on fractional calculus. Now, in typical calculus, you have a function f of t, and you can take its derivative df by dt, or even a higher order derivative like the d2f by dt squared, which is the second derivative. But what if I didn't want to fully commit to taking a derivative? For instance, what if I wanted to take a fraction of a derivative? Well, I can do that using fractional calculus. Fractional calculus allows me to take a half derivative, or a quarter derivative even if I wanted to. In general, using a combination of clever manipulations in the gamma function, I can compute fractional derivatives like the alpha derivative of f with respect to t, where alpha is some real number between 0 and 1. In fact, it could also be a complex number, so even though it says fractional calculus, I'm not necessarily restricted to derivatives of a rational order. So a fractional differential equation is then a differential equation which involves these fractional derivatives. Anyway, that should do it for this brief video. I'd like to thank the following patrons for supporting me at the $5 level or higher, and if you enjoyed the video, feel free to like and subscribe. This is the Faculty of Khan, signing out.